We're on the air. Okay. Now, what should be clear by now is that if you use overlays, then you just have this logical data structure that is mapped on, let's say, the internet. And the easiest way to think about this problem is just a big network like the internet, and then you have this logical overlay, which means that your logical neighbor could be at the other side of the internet. Now, that may be a problem if you're concerned about latencies. So what people have been thinking about is, may it be possible to make sure that I still have this logical organization, but that I choose my neighbors in such a way that they are also, let's say, physically close by. Because then if you would route through your overlay, you would be making hops that kind of correspond with the underlying topology. So that's the problem here. Okay, so you got to watch out that you actually have erratic messaging through your network, because you may be my logical neighbor at the other side of the world now. If you then have to forward it to your next logical neighbor, who will be then next to me, we will just be bumping messages back and forth. Oh, what is this? Okay, sorry about that. So let me just throw up all of these things. Now, what people have tried to do is come up with topology-aware node assignments. Okay? So what you do is when you actually hand out an identifier, you make sure that that identifier matches something that is also topologically close. The point is that it can be very difficult. To give you an idea, so far, when you are generating an identifier, you just basically flipped a coin, right? You drew a random number. What you would then have to do is to not draw a random number, but a number that corresponds to your position in the underlying network. Can you imagine that that may not be so easy to do? Yes? Why don't we use the normal routing protocols on the internet? So OSPF is a shortest path Dijkstra solution. Why couldn't you do that in an overlay network like a distributed hash table? Who has an answer to this? It's an interesting question. Yes? You don't know the old topology. So let's give a concrete example. Let's take chord. Okay? Now, try to think of your question in terms of chord. I have an overlay network, and it is organized as a logical ring. Okay, so I'll just repeat what you just said to record it. You may have to renumber all the nodes. In fact, you don't need to do that. There's another problem. Yes?
I don't think that's any separate part of the world.
Okay, so what you're saying is that proximity in the ID space prevents that you can effectively actually apply Dijkstra, because it will, if you use that as a proximity metric, you're still in trouble. Yep. Okay, so another thing is that you would have sparse parts that you would not be able to get together. So I'm gonna add some confusion to this. What you can do is, first of all, you can use a different proximity metric. The ID space is okay, but hey, it's a random ID space anyway. So what I can do is I can measure delays between nodes, right? If I discover a node, then my cost between me and that other node, well, it's just a matter of delays. Yes?
Isn't the delay that's not really constant?
Let's make the assumption that the delay is even constant. And watch out, I'm pulling your leg. No, let's just think of routing. Let's keep it simple.
Proximity is are preserved.
So basically you're saying, okay, if you just boot everything, let's say in a random graph or whatnot, and then you try to construct a ring.
Yeah, you will always use a lot.
What is wrong in the entire reasoning here?
It's already a graph.
It's already a graph. It starts with that, okay? So I have my logical ring, and that's what I have. What about my nonsense about measuring the delays? None of you noticed that, well, you could do this. Are you going to do this for all pairs? Good, let me do this for all pairs. Why would I use Dijkstra after that? Because then I've discovered all my neighbors, which are n minus 1. Okay? And here's the big problem. In the overlays that we're considering, we're assuming potentially 10,000s of nodes. You don't do Dijkstra with 10,000s of nodes. That doesn't scale. So the whole idea is that if you would enforce any overlay structure, and even if you would take a random graph, okay, that by itself would be fine. You can actually measure delays over the links in that random graph, and provided that that random graph is not too big, you could do Dijkstra. Or what you could say is, if the overlay is so big, let me organize it as in an OSPF, where you have a hierarchy of networks, and then for every one of these networks you could do Dijkstra. But that's a completely different situation. The situation that I have over here is a huge bunch of IDs and nodes that want to talk to each other. And what I'm doing with the finger tables is actually creating the shortcuts, and the only thing that I'm missing is the fact that I'm not using a network realistic distance metric. That's the problem. Okay? Does that answer your question? Okay. Now, another thing you could do is do proximity routing. Now, what you do is essentially you maintain more than one possible successor, and I think I hinted at this last time. So in Chord, normally what you would have in the finger table is that this entry would point to the first node in this interval. Okay, you're really taking the first node that you know. But what you can do is you can store many other nodes in that interval, provided that you know them. And if you would measure the delays to each of these nodes, you would be doing just as fine as well. And what I'm suggesting here is the following. What I'm trying to do is throw my request as far as possible to the node that I know who is not responsible for that key. I want to get as close as possible until I hit certainty. Now I know the node who is responsible for that key. But if I happen to know more nodes in that whole interval that still have an identifier less than that key, I'm still doing good. Okay? And then I can deliberately choose a node that is physically closer to me and forward the request to that node. I'm still doing fine because I'm meeting the requirement that I'm not overshooting my request in the sense that I'm passing it on to a node that is overshooting it by passing the request to a node that is beyond the key, who may have a predecessor that is closer to that key and still larger than that key. Okay? Now, one that you cannot do in Chord, but which you can apply in a system called Pastry, is a proximity neighbor selection. I have some information on that on the book, but I won't delve into any details over here. If there's a choice of selecting who your neighbor could be, if there is a choice, you pick the one closest to you. And Pastry has this. Essentially what Chord does, it tries to get as close as possible to a key by means of its successor function. And what happens in Pastry is that you pick a node and you look at its neighbors, and then you decide on which real neighbor you're going to take. And that's where you have this choice of picking the one that's closest to you. In general, exploiting network proximity is a nasty problem in overlay networks. And did you send me this paper on Dropbox? Yes. It's actually, that was an interesting read. Let's take Dropbox as an example. Does everybody know what Dropbox is? Are there people who do not know what Dropbox is? Oh, very good. Okay. So, very briefly, Dropbox is nothing else but a storage system somewhere in the cloud. And you could argue that you as a client using Dropbox essentially establishes an overlay network. And what this paper shows is that Dropbox does automatic synchronization. All of these Dropbox-like systems have a very simple model. You have your folder on your desktop or whatever, but underneath there's actually a process that continuously synchronizes that folder with that other thing in the cloud. And the synchronization is an important thing because that's where latencies could emerge. And this is where you see that the overlay is actually there. Now, exploiting network proximities in a general overlay is actually kind of nasty, in a structured overlay, I should say. And an example of that is Dropbox, where they identified that the major problem is really with the fact that Dropbox uses servers on the west coast of the United States. That introduces latencies for lots of people, and by doing all kinds of measurements, you can see that it's actually a significant latency that could actually harm you, so to say. Okay, so it is an important topic. You could argue that in general overlays, it really depends on how you use the overlay, whether you're dealing with a serious problem or not. And Dropbox is an example where it could actually be a problem if speed is an issue. Okay, that's all I wanted to say about structured overlays. Yes? No, I discussed it here as exploiting it in structured overlays. In unstructured overlays, there's much more flexibility on choosing to whom you're going to send the file to. And what I'm only dealing here with is a structured overlay, and that overlay can have nothing to do with the underlying overlay. So it's easier to explain it like that. Okay? Otherwise, you're absolutely right. An unstructured overlay will links continuously change. Yeah, that's the best way of looking at it. You have many more choices of deciding who's going to be your neighbor. Okay. I want to talk about something completely different. I want to talk about a hierarchical location service. And it is, I'll be explaining what we actually did, but it's a very representative example of many hierarchical location services out there. The idea, again, this continues to what we're talking about. I have a more or less random identifier, just, a bunch of bits, a bit string, a random bit string. And what I need to do is I need to find the corresponding IP address, or more formally a contact address. In the case of a distributed hash table, I translated that to a key belonging to a file. And now let's look at something else. Let's take a look at mobile agents again, and I just want to know the contact address of my mobile agent. Or even perhaps again of a replicated file. And now I'm assuming that a contact address is associated with an IP address. For example, of the server holding that replica of the file. Now what you can do is you can simply build a tree on top of the internet. And again, watch out, because the next few slides I'm going to be pulling your leg. Okay? And in the end I'll be asking you, hey, didn't I just introduce a scalability problem? And if you say yes, you're in good company, because lots of my colleagues actually said, oh man, you got a scalability problem. Okay, just watch out for this. So it's actually very simple. I'm taking an identifier, my random bit string. Let's assume that I have a mobile agent, or I have a possibly replicated file. Down somewhere in the internet, this file has been stored, and where it's stored has an associated contact address. Do I have the contact address? I can get to the file. So what I can then do is I can organize my internet in a hierarchy where I have a root node, then I have subdomains and another subdomain, etc., etc. And each of these subdomains, here's an important assumption, corresponds to an area in the network. It's easiest to think of this as a geographical area, but because geographics don't always map one-to-one to my network topology, I should strictly be speaking about a network area. Okay, but the mindset, if you take a geographical area, is the simplest. And then what you can do is the following. You take the address of this entity E, file, mobile agent, and you store it in a leaf node or an intermediate node. The intermediate nodes contain a pointer, and again it's like this. You're in the root, and let's assume one contact address, and the root says, no, take the left branch. And then you get an intermediate node, that guy is over there, over there, over there. And then basically you get a binary search. Okay? In the case you have a replicated file, you may have that thing is in two domains, and this is where you have stored the file, and then you have contact addresses. And what happens is that somewhere, namely at the intermediate node that is common to both of the sub-branches, you store two pointers. This file is over there as well as over there. You know, have your pick on which branch you want to take. So I hope that's fairly straightforward. So we have pointers over here, over there, over there, over there, over there, and we have contact addresses, or the actual file, I would say, in the leaves. Okay? So far, so good? Now watch this. Let's first do a lookup operation. So I'm over here, and let's assume I have a non-replicated file that is over here. Then what I do is I insert my lookup request here at the leaf, and leaf says, never heard of this guy. Let me ask my parent. And now you have to realize that parent covers a larger area. If that parent says, hey, I don't know where this guy is, it forwards it to its parent. And what happens as soon as you hit the parent that actually knows the node, or the file I should say, your request will be then forward downwards the tree again. Got it? Very important observation. My request will not leave the area that contains the file and myself. So depending, of course, on the organization of the tree, it never leaves the area, the smallest area wherein my request and that file actually lies. So that's the locality principle. And like I said, it's easier to think in terms of geographical locality rather than network locality. Yes?
Can easily be combined with the previous hash, distributed hash stuff. You make every...
Let me first repeat your question. This can easily be combined with the distributed hash table stuff, I think you said.
Yeah, you have every geographically limited space, one of these nodes.
In principle, yes. The thing to keep in mind right now is that I'm still talking about a single identifier. Okay? And then, but you're right. But keep this in mind for just now. Okay. If you have an insert operation, it's exactly the same thing. So let's assume I had my file over here, and I want to insert a copy of the file over here as well. So what I do is I say, hey, insert a copy of the file. The request goes up the tree until you hit the first parent that knows about this file, and then it says, okay, I'll register pointers to you. And then you go down the branch again, and again you see that your update request will not go outside the smallest area common to where the file already was, the closest replica, you could say, and where you want to insert it. Again, a locality principle. Okay. So when we built this thing, people said it will never scale because the root knows all. Does the root know all? Why not? Not all requests are forwarded to the root. But if I would have a single root, that root would need to know about all identifiers, I guess.
I think it might be enough if the root only knows domains, so not every single.
But suppose that I'm looking for a file at the other side of the world.
Well, then it knows to go that way or that way.
Yeah, but it should know about that file, right?
But does it need to know about the whole thing, the whole file?
No, just needs to know about its identifier. So now let's assume that I have 10 billion files in my system. That means 10 billion identifiers.
Maybe you don't need the whole identifier, but just a part of it. Like
No, you need the whole identifier. Because it is a pure identifier, and it has no information in it, so it's just a random bit string. But watch out, because I'm pulling your leg. You first.
Can we apply the B plus tree search philosophy?
Say this again?
Plus tree search philosophy when you say the root has one key, right?
Uh-huh.
And I'm looking for a key, let's say the root has 500, the key, and the key I'm looking for is 900.
Uh-huh.
So it says it has two pointers, let's say it's number 3, and it says if you're lower than 500 when you're looking for, go on your left.
Okay, so let me try to rephrase your question. Can't we use your example is a B plus tree? It could be anything. Okay, it's a tree based on the content of identifiers, and then the whole idea would be that you would divide your identifiers over the different branches of the tree. Yes, you could do that, but that would not be a location service. Because I want to stick to the, it's not that I need, it's not that the problem is that I want to store the identifier with its associated contact address, because hey, I could use a structured peer-to-peer system for that, right? What I want to do is stick to the principle that I want to avoid that my requests go to the other side of the internet when the file is actually close by. Yes?
And do you think that you do have a problem, or they're pretty easily solved? I think that the root in the first instance does need to know everything, but you can cache them out and you can send information back to the
Okay, you can have caching information, okay?
interesting node. They're pretty easily solvable.
DNS caching using
So there's one reason why you can't use DNS caching, and I haven't explained this, but it is in the book, is that I should be able to assume that the mapping between identifier and its contact address should be able to change fairly rapidly. So if you think in terms of a mobile agent, it's tuck, 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 tuck. And what I need to support is that the binding between an identifier and its address should be able to change rapidly. DNS cannot support that, or is not made to support that. But you haven't noticed how I've been pulling your leg.
The identifier can be named of combination of the identifiers of the intermediate node.
No. So the identifier can be a combination of the things you stored in the intermediate nodes. No, I don't want that. The identifier is a bit string. I don't want to make use of the structure of that bit string. I made a crucial step when I said to you, hey, doesn't the root need to know about all identifiers? And before I was saying, hey, I'm having a single tree per identifier. Yes?
Yeah, I'm not following everything, but I was thinking that if you have two child
You want me to repeat that part as well, or just...
if you have two child nodes, can you forward the request to one of the child nodes?
Right.
One of the child nodes says, well, it's not here, then you can infer that it's on the other side, so the root doesn't need to know all that.
No, that's an optimization. Namely, if you could learn about where you were previously. So, for example, if I ever looked up this thing, I looked up this file over here, then these guys can start storing pointers saying, oh, it's over there, I can instantly forward at that. But that's not what I'm hinting at. There was somebody else. Yes?
I wanted to say that, for example, because of the structure of the tree, for example, I mean, this could apply only, could be applied only for the root because the other thing, because the request has already gone to that, and the root knows that, for example, the site from which the request comes doesn't have the file needed.
Okay.
And it's, I mean, the request can come either from the left or from the right. If it comes from the left, then it knows for sure that it's not, that the file is not on the left.
Okay, so I'm not going to repeat that entirely. Again, it has to, it's kind of an intelligent, not caching scheme, but keeping things in mind where things came from. Now, let's forget about a single root knowing about all identifiers. This is a single tree for a single identifier. And if I have 10 billion identifiers, why can't I have 10 billion trees? What?
There is no need not to have that relationships because if you take a look at the multicasting, for example,
Yes?
each client that wants to multicast has an option to build its own multicast tree. And it will have local.
No, if I have, so there are two extremes. I need one tree for all identifiers, or I have one tree per identifier. Okay, and yes, you could do something in the middle. Why can't I just, let me start with one tree for all identifiers. Why can't I partition the root? Using a simple hashing function. That gives me, how many roots do you want? 1,000? Let's have 1,000 roots. Okay? And what I can do is I can spread these roots across the internet. Got it? You see my point. Why not? Everything is deterministic, so I even know where the roots are. Okay? Likewise, I can apply the same partitioning scheme on intermediate nodes. And what is partly explained in the book is that I can apply a location-aware scheme to decide exactly which node will now be responsible for which identifier, not based on the content of the identifier, but for example where it was created. And you can have these columns of servers, and by a column I mean that it actually serves as a leaf node. It's one single server that acts as a leaf node, an intermediate node, another intermediate node, another intermediate node. Oh, and by the way, it is also a root. And then you may have the optimal case that if you're doing a lookup exactly in your column, hey, you're moving only your requests within one machine. And then when you're over there, it's, hey, to the other side of the world. Turns out if you do this and you run some simulations, you can actually have a performance improvement of at least a factor 2 to sometimes even 10. But it all depends on access patterns, and that's where the tricky part comes in.
On what basis you are going to do routing? You have this topology.
Well, you're not doing routing. You're doing the routing within the tree. So the tree structure is there. Okay? That's a very important observation. It is by itself just another overlay. You know exactly how to do the searching and the insertion within that overlay, which is a tree. So that means you'll always be there. But the problem is, how does this thing map onto the internet? First observation, you could easily make this scalable by just instantiating as many roots as you want. That's not the problem. And if you then organize all these nodes according to access patterns for files, you may actually have a very efficient scheme that resembles the network proximity schemes I just discussed with structured peer-to-peer.
So you're not splitting the space in a hash ordering, preserving.
No, so what I just suggested is by just using a hash function, you can partition the roots. And what I said is, because that is still completely independent from the actual network topology, I am at complete liberty to decide which root I place where. And by looking at access patterns, I can decide on the optimal placement of these, call it hashed routes, and hashed intermediate nodes. Yes?
So when you say that you have multiple routes and multiple trees, these don't have to be physically separate trees.
Right.
So one node
Right.
can act as a leaf in one tree and a root in another.
Right, exactly. The take-home message here, this is the most important one. You have to separate the logical design from the physical design. That's a mistake we make continuously. Yes?
This is just like the purview and spanning tree, only static.
It's like a?
Purview and spanning tree. So we have the spanning tree, static.
A per VLAN spanning tree. I would have to think about that if it's exactly the same. I don't know exactly. Okay?
So when you, as a node, get a request from a file you don't know, how do you decide which tree to look at?
You have to keep track. I haven't explained that. Can you just assume for me that there's a very efficient, not even very intelligent trick to do that? Okay, you have to keep some administration of who your parents are. Basically, what you need to know is the hashing scheme applied by your parents. And that's what you maintain. Oh, it's that thing? Oh, that means that parent over there. Not this one over here. Okay? Basically, you're maintaining a fat tree for those in computer architecture. Okay, let me move on to namespaces. Let me see how I'm going to do this. Yes, I'll briefly go through this because it's a bit of an abstract thing, and you'll instantly recognize that I'm talking about the namespace of any reasonable file system or even DNS. Now, what is a namespace? It is a graph where a leaf node actually represents your named entity. We call it a file. Okay, and just think of files. That's the easiest thing. And then you have a directory node. Hey, we all know about these guys. That refers to other nodes. And then you get this scheme. Here you have your graph. You have nodes over here. These things are directory nodes, and here are your leaf nodes. Okay? And what you normally have, take a look at this name over here, is that this name comes from the labeled edges that lead to that node. Doesn't this look like a file system? As you would do in any reasonable file system. Now watch this. This is kind of important. So your directory contains edge label node identifier pairs. Okay? And watch this. This is a namespace. And now I'm talking about node identifiers. There seems to be something tricky going on. Now, you can add all kinds of attributes in all of these nodes. We all also know this from file systems: type of the entity, an identifier for that entity, address of the entity's location, whatever, okay? And of course, the directory nodes can have attributes as well. And for those familiar with file systems, you know this. Directories in Unix are special files, and they contain all kinds of information on basically what they're pointing to. And this holds for any reasonable file system. Now, let's start resolving names, because that's actually the more interesting thing. So, here comes a tricky one. To resolve a name, you need a directory node. And I can go over here. If you want to resolve this name, you start over here, you do this, that. And you can do this by going to every one of these nodes saying, listen, what's this part of the path name, okay? So you start over here, you have home. You ask N0 where home is, says, go ask this guy. Now you're at this guy, he says, okay, give me stain. Oh yeah, go to that guy over there because he knows more about stain. And then you go to mbox. Okay. So in order to resolve a name, I need to go to a directory node, to the root one. How do I find the initial one? Yes? Yeah, that's basically, put it in a standardized location. You can't name it. I hope you agree with me. Okay, and that's basically what's on this slide. And what you're suggesting is a standard location, that's all fine. What is the whole issue? You know beforehand how to start. And how to start is something that is separated from your namespace. That separation is called a closure mechanism. So if you want to resolve a name in DNS, how do you do this? Well, once upon a time, you configured your system to go to your initial DNS server. And that, by the way, was identified by means of an IP address. You have that good, it's completely outside of the DNS system, but from that moment on, you can resolve names. If you take a look at a file system, the root is hard-coded, quote unquote, in the operating system. If you use the change root command, okay, you can change the root. I explained this with Planet Lab, right? But what you basically are doing is saying, this is my root, or that is my root. And you record that information, and from that moment on, the name resolution mechanism works. Yes?
We can actually name the root, but cannot reference it by the name when we try to...
Very, very well put. So we can name the root, but not using the same namespace in which you are going to resolve names. So you need a separate namespace to name, for example, a root.
Yes, but I can also name the root within the same namespace, but I cannot use that name to resolve.
Okay, you're right, you can also name the root again, but...
As I'm plugged into that namespace, as I have entered through the root, I could...
Yeah, that's true. You could always, of course, name your root, but in order to start the first name resolution, you have to have a naming that is outside the namespace in which you will resolve your name. And that is actually an answer to this question, why are closure mechanisms by definition implicit? Because, you know, you have to start somewhere and it has to be outside your namespace. That's the problem. And here are some examples of this closure mechanism. I just mentioned, you know where your initial DNS server is. You know where your local NFS file server is to start. Here's a phone number, a very old one actually, because we don't have the 444 anymore. And you know where to start. And again, here's an IP address, and hey, it's hard-coded on how to find that IP address. Yes?
That makes your example that you just gave by changing the root.
Yes?
System, by definition, has to be virtual. Because you're doing it in the namespace of the file system.
Exactly. So if you apply the change root command, it has to be that you have a kind of virtual root, and at least there's a small namespace on top of that for which the change root command would work. Absolutely correct. Absolutely correct. Okay. Let me see where I am. Let's take a break right here. Yes, I'll get to your question after the break. Okay.